Hi class, it's the 10th week of our survey research course. Now that you have a draft of your survey instrument, it's time to talk about how to evaluate the quality of your survey and how to make improvement and get the final version ready. As an initial step, you need to have the draft survey reviewed by two groups of people. The first group consists of experts in survey design and in your subject field. The second group should be people from your target population. Together, you need around 10 individuals from the two groups, and you need to ask each of them to go over every item on the survey and provide very detailed comments. If you ask them to provide comments in writing, make sure you print a version of your survey with plenty of room for them to write, or you can work with them in a question and answer session using Think Aloud protocols. Either way, the goal is to gather input from different perspectives that can help you identify the parts or elements in the survey that are confusing, incorrect, or misleading. You then revise your survey based on their comments. After the initial revision based on the feedback from the two groups, the next step is to pilot test the survey instrument. During this step, you will ask a group of people, somewhere between 25 to 75 respondents, to complete the survey in the data collection mode as you would have set it up for real data collection. The pilot run will allow you to estimate how long it will take a respondent to complete the survey or interview. In addition, the pilot data you collected can be used to test the quality of your survey and allow you to finalize the questions for data collection. If you get a sufficient sample size in the pilot test, you can use the pilot test data to run some basic checks on the questions using item analysis and factor analysis. Both of the procedures will be discussed in a separate video. Once the final revision and improvement are completed, the finalized survey should consist of questions that are clear, no confusion, and with as little bias as possible. The presentation of the survey should be welcoming and easy to follow. When I say that questions should have as little bias as possible, the word bias is defined as the inconsistencies between the real values and the observed scores resulting from the survey. After all the efforts we have put into the survey development, the ultimate goal is to reduce bias and improve accuracy. In order to reduce bias, we need to take into consideration two types of errors. The first is random error, which is caused by temporary components that may impact the values of the measure. For example, a respondent may rate life satisfaction higher when he or she is in a good mood, but the rating would be lower on occasions where he or she is in a bad mood. The second type of error is called systematic errors, which are caused by method effects or conceptual shifts in questions. Random errors are mostly uncontrollable, so the goal is to minimize systematic errors. How do we know whether there are biases or how much bias is there in the survey instrument? It's a good question, but not easy to answer. In measurement theories, there are two ways to evaluate measurement bias: reliability and validity. Reliability is about the consistency in the results, regardless of variations in time or location of the data collection. A question or instrument is reliable if it yields consistent results. For example, if a respondent changes her answer every time she's asked the same question, the question is unreliable. Remember that we use a battery of questions to measure the same construct. The battery is considered as a reliable measure of the construct if the respondent's answers are consistent for all questions in the battery. There are a number of ways to measure reliability. We are going to talk about the four most common reliability measures, including test-retest reliability, parallel form reliability, split half, and Cronbach alpha. First, if a researcher can afford to have the same group of respondents take the survey multiple times, the test-retest reliability can be used to measure the reliability of the survey. Mathematically, the test-retest reliability is simply the correlation between the two sets of scores obtained from having the same group of respondents take the same test twice over a period of time. If the correlation is high, it's an indication of high reliability. The tricky question about using test-retest reliability is how long a delay should be given between the two tests. If the time interval is too short, reliability may be overestimated because the respondents still remember their answers from the first time. If the time interval is too long, people's answer may change because their attitudes have changed, and thus cause the question's apparent reliability to be artificially low. Second is a parallel form reliability. Parallel forms are defined as two forms or two separate survey instruments that contain different questions, but they measure the exact same thing. The same group of people take both forms, and then the correlation between their scores on the two instruments is the parallel form reliability. Higher correlation indicates better reliability. The challenge of using this approach to estimate reliability is that a large set of questions that address the same construct have to be created. They will be randomly divided into two sets, and the assumption is that the randomly divided halves are parallel or equivalent. Both test-retest reliability and parallel forms reliability are hard to get because it's rare that a researcher has a chance to ask the same group of respondents to complete a survey instrument on two different occasions or at two different times. As a convenient alternative, the third option we have is the so-called split half measure of internal consistency. This type of measure of reliability is applied to the group of questions that measure the same concept. In other words, if you have an instrument that measures several different concepts, you cannot use the split half to measure their internal consistency. However, if you have 20 questions and all of them are designed to measure the same concept, what you do is to randomly split the 20 questions into two halves, with each half consisting of 10 questions. Each respondent in the entire sample will have two scores, one from each half. The correlation between the two sets of scores from the two halves is the value of the split half measure of internal consistency. Finally, the most common measure of reliability we encounter in the literature is called the Cronbach alpha. Cronbach alpha is literally an average of all possible split halves of an instrument. How many ways can you split an instrument of 10 questions into halves? 30,240, which means there are 30,240 split half measures. The average of the 30,240 values is the Cronbach alpha value. Since Cronbach alpha is based on split half. It can only be used to measure internal consistency of instruments that are unidimensional. In other words, that measure a single concept. Also, because Cronbach alpha is essentially a measure of correlation, it has a value somewhere between 0 and 1. The closer it is to 1, the better. The guideline from the textbook is to look for a alpha that is greater than 0.8, whereas anything below 0.6 is considered unacceptable. What if you believe your instrument is unidimensional, but the Cronbach alpha is low? First, check the correlations between items. It raises a red flag if there is a question that has low correlations with other questions. Second, you can also run Cronbach alpha repeatedly, each time with one of the items removed, and see which ones are causing a problem and remove them from the instrument. Let's move on to validity. Validity is a more elusive concept than reliability. The definition is that a valid instrument should measure what it is intended to measure. When people talk about validity, it sounds like a number of different ways to capture validity are possible. But validity is actually quite hard to measure. Let's start our discussion with the very basic check of validity. It's called face validity, which just means that you look at items on the instrument and provide a subjective evaluation about whether the items seem to be measuring what the instrument is designed to measure. Content validity is a better defined validity type than face validity. Content validity is about measuring all different aspects of a construct that a researcher intends to measure. In other words, a number of questions are used to measure different aspects of an underlying construct, and the degree to which they measure all the important aspects of the construct is called content validity. Let's use depression as example. Depression as a construct has 7 dimensions based on the literature. In order to have content validity, an instrument measuring depression need to have questions that sufficiently capture all 7 dimensions of depression as identified in the literature. Remember that both face validity and content validity are subjective evaluations of validity. Convergent and divergent validities are two measures that can yield numeric values. For example, one instrument is developed to measure depression related to social media use, and another published instrument measures depression in general. Because they measure very similar constructs, if you have the same group of respondents complete both surveys, a high correlation between their scores on the two instruments is an indication of convergent validity. However, if there's an instrument that measures depression and there's another instrument that measures motivation, because those two are very different concepts, even when the same group of people complete both surveys, a low correlation is expected between the two sets of scores, which is an indication of divergent validity. If a high correlation is found between instruments that are supposedly measuring different concepts, it's a sign of problem with one or both instruments. Criterion validity is about how a measure is related to the intended outcome. Criterion validity can be quantified in two different ways. One is concurrent validity, the other is predictive validity. Both of them are based on the correlation of the scores from an instrument and some measured outcomes it's intended for. For example, if a group of high school students took the ACT/SAT test to measure their academic aptitude, the correlation between their test scores with their high school GPA is evidence of concurrent validity. Let's assume that those high school students later went to college and their ACT/SAT scores were correlated with their college GPA. In this case, a high correlation can be used as a support for predictive validity because ACT/SAT test scores show the predictive power of their academic aptitude in college. The last one is construct validity. Construct validity is about the degree to which an instrument measures what it claims to be measuring. Some researchers believe all other types of validity we have talked about should come under this big umbrella of construct validity because they all serve the same purpose of making appropriate inferences of survey results or test scores. In other words, researchers have to make sure that they are measuring what they intended to measure before the results can be interpreted and used appropriately. There is no mathematical formula to quantify construct validity, but the operationalization of concepts and constructs during the survey development stage is the foundation to claim construct validity. Even though validity is an important measurement concept, it's important to understand that it is hard to give a numeric value to most validity measures. Our last topic in this video is about sampling error and sample size. Remember I said that the larger the sample is, the better. It's a point easy to explain. In quantitative research, our goal is to make inferences about the population based on the data collected from samples. The larger the sample, the closer it is to the population we're trying to study. Since in most cases we're not using data from the entire population, the sample as a small fraction of the population inevitably results in sampling errors in the research findings. Larger samples better approximate the population and thus reduce the room for sampling errors in statistical inferences. Another approach to improve accuracy is to use probability samples. In week 6, we talked about how to get either probability samples or non-probability samples. If a probability sample is used in a study, there are ways to estimate the errors mathematically, and corrections can be made during the process of making statistical inferences. However, such mathematical manipulations are not possible if non-probability samples are used. If you recall, statistical inferences based on sample data introduce two types of errors in statistical analysis. They are conveniently named type 1 and type 2 errors. Type 1 error is the rejection of a true null hypothesis, and it's also called the level of significance. For instance, a type 1 error is made when a researcher concluded, based on the sample data, that there was a significant difference between the math scores of middle school girls and boys, when in fact there is no gender difference in the math achievement level in the population of middle school students. We usually set the probability of making a type 1 error at an alpha level of 0.05. But it can be higher or lower, depending upon several factors such as sample size and effect size. Type 2 error is the probability of failing to reject a false null hypothesis. For instance, high school girls have higher anxiety about their body image than boys in the population. But a researcher failed to find any significant differences based on a sample dataset. Be clear that the type 1 and type 2 errors in statistical analysis are not related to the random and systematic errors that we previously discussed in the evaluation of survey questions. Because there is always a chance of making type 1 and type 2 errors in statistical analysis of samples, we can never prove anything with statistical evidence. In order to reduce the chances of making errors, we need to increase the statistical power, which is the probability that a true hypothesis is accepted. Mathematically, statistical power is 1 minus the probability of making a type 2 error. When you need to estimate how large a sample you need, these are the factors you need to consider. What is the alpha value, which is your level of tolerance for making type 1 errors? What is your estimated statistical power? How much variation do you expect to observe in the population? And what is the estimated effect size? Once you have an idea about these factors, there is free software available to help you estimate the minimal sample size needed. That said, the bottom line is to always try all you can to increase your sample size.